Hi everybody, this is Peachy from your WCA Astronomy class, and I'm doing a second podcast today for your Life Cycle of a Star unit. If you have not seen the first one, you should watch that prior to this because right now I will just be focusing on low mass stars. So today we are going to be looking at the stars that are kind of in the realm of our sun, as well as the ones that are smaller and maybe just a little bit bigger. Remember that any star that is found in this Hertzsprung-Russell diagram on this main sequence is a star that's in the prime of its life. So stars will fuse hydrogen to form helium and release energy in a process called nuclear fusion. And when it's doing that, it's just busy being a star. You know, it's not forming, it's not dying. And we can look at this as a relationship between brightness and temperature. In general, the brighter the star, the hotter the star. The dimmer the star, the cooler the star. And that's what this graph represents. But it also shows us that stars don't always follow this relationship. When stars are in the process of dying, you then can have some very, very bright, cool stars and some very, very hot, dim stars. So they outlie that relationship. But that these stars here and here don't represent the main population of stars. They represent stars that are in the process of dying, going through that death cycle. Okay. So today, like I said, we're going to focus on stars that are in spectral classes, basically G, K, and M. These would be red dwarfs, yellow dwarfs, orange dwarfs. These stars are going to be kind of medium-ish in, medium to cool in temperature. Cool is relative, by the way. Obviously, it's not cool, but it's the coolest of the stars. And if you look at the electromagnetic spectrum here, you can kind of see the relationship between color and temperature. When you have waves that are on this end of the spectrum, and that would include the red visible light, that is going to be your least energetic and lowest temperatures. So you can kind of think of these waves here. Look at how long the wavelengths are. The longer the wavelength, the less energetic the wave is. I always try to picture that every time a crest comes past you, it's kind of hitting you. So you can even think of it as standing, at the beach. If the wave comes, it can almost like knock you back. If the waves are spaced far apart, you're getting hit by this wave, and then it takes a while, and then the next one comes through and hits you again. And so you're able to kind of stay standing. If those waves were coming in like boom, 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 really fast, it would probably knock you flat over because every crest of the wave is just another kind of punch of energy that's hitting you, right? So the shorter the spacing is between the waves, the shorter the wavelength, the more energy you are going to receive. These are short frequency but high energy waves. These are low frequency but low energy waves as well, okay? And the colors are representative of that. Red color means cooler or lower temperature. Blue would be hotter or higher temperature. And I try to tell people too that if you're familiar with like a campfire or a Bunsen burner is a great example, but I know we don't use those as much on online schools. The flame on the outside is often yellow and orange, and it's not as hot. Even a birthday candle would be a good example. So if you're like, oh, I can put my hand through the fire, I'm so cool. You barely run it through the outside of the flame because that's the coolest part of the flame. You wouldn't go right next to the wick where the flame was blue because that's hot. So we can see that as well in examples that we are familiar with just looking at fire. So a low mass star like our sun is a medium. It's called a yellow dwarf star. By the way, dwarf is one of the words that I have a super hard time saying. I know it's dwarf, but I oftentimes say dwarf. So just maybe you want to count the number of times that I say dwarf instead of dwarf. I will try. So this is, of course, the nearest star to us, and it is a yellow dwarf star. It is about 6,000 degrees on its surface. So that visible part is about 6,000 degrees Kelvin. And the core, which we can't see, is going to be roughly 10 to 20 some million degrees Kelvin. So it's hot. It needs to be super hot and a lot of pressure in order to kind of bypass or overcome that strong nuclear force and force those two atoms of hydrogen together to form a single heavier atom of helium and release all that energy. Okay, so that is an important part, right? When you look at the life cycle of a star like our sun, it kind of follows this here. Our sun is right about here, 4.6 billion years old. It started off as a protostar, and it had this protoplanetary disk around it. Once nuclear fusion began, it would have given off this initial burst of energy, and it would have actually been enough energy to kind of blow away a lot of that initial dust there. Because now we have something called the solar wind, which is basically these streaming or these particles that stream outwards from the sun all the time, and they're responsible for forming the tails on the comets, and we are bombarded by these particles all the time. And if it wasn't for our magnetosphere and stuff, we would probably have a lot more radiation on Earth that would harm life. So it's a great thing that we have this magnetic field that surrounds us. But that would have initially gotten rid of much of that protoplanetary disk, the dust and gas that surrounded us. What was left behind was the heavier bodies, the sun and these planetesimals that would have eventually kind of stuck together to form larger planets, meteors, asteroids, comets, that fun kind of stuff. Now, as the sun kind of goes through this stage here, all it's doing is it's fusing hydrogen into helium and making energy. It's right here. Now, it's kind of a misconception here, guys, to think that the sun is going to somehow progress along here and move. No, that doesn't happen. The sun's going to stay right where it is, right there. It's going to stay there for a long, long, long time, this whole length of time here, right? And eventually what's going to happen is that hydrogen is going to run out. We're not going to have any more hydrogen in the core. The outer shell, the outer layers of the sun will have hydrogen in it. It doesn't, because it's not hot enough to fuse there. So even though we have still a supply of hydrogen in these older stars, it's not in the area in the core where the temperature and pressure is great enough to overcome the strong nuclear force and actually force fusion to happen. So we're only talking about the stuff in the core here, okay? So when all that hydrogen is used up, what happens is, it's out of gas. So what are we going to do? Well, first we have to remember this whole process here called hydrostatic equilibrium, right? And we talked about this in my last podcast, but I want to make sure you guys really remember this. Hydrostatic equilibrium. That's what's going on here, okay? The outward force of this, basically these fusion bombs going off in the core of the star is balanced by the inward pull of gravity. Gravity is determined by the mass of the star. So we know that gravitational force is not going to change. What does change is that fusion force in the core. So if you can imagine, if these things are in balance, that means the star is staying in a state of equilibrium. It's not changing in size. It's not changing in temperature, really. It's kind of staying the same. Once the it's the outward explosion force of the fusion, once that thing stops because, we're out of hydrogen, then you got to think, what happens? Okay, so if this is stopping inside the star, this guy, these arrows pointing out stop, all we have is arrows pointing in. So if all we have is arrows pointing in, the star is going to shrink. It's going to be compacted. And guess what happens? Pressure increases, temperature increases, so it's going to get hotter. So now it's hotter than it was before. It has more pressure than it was before. So now what it can do is it can take those helium atoms and it can force those guys together. And it can make helium, actually, if you squish the helium together, helium will be combined to make, I think it's carbon is the next one, isn't it? Don't remember, but I'm pretty sure it's hydrogen, helium, and then carbon. So in any case, then you'll end up with that, right? And so what's happening is that because this is a more energetic reaction, you know, you're actually taking heavier elements and forcing them together to make an even heavier element. It takes more energy and it gives off more energy. So it's given off more energy. So now suddenly these arrows inside, they're bigger than they were before. I'm going to draw another arrow here with my fancy tools. So we're going to add another arrow pointing outwards here. So we get a bigger arrow. So the star expands. And that's where we see this red giant. Okay, so the red giant is occurring after a shrinking stage. So really we should insert a shape here. We should insert a little guy right in between, because the star actually does shrink first. It shrinks before it becomes a red giant. And then, if it's a small star like our sun, it will eventually go through the same process a second time, right? It burns that helium into hydrogen. It doesn't have as much helium. It has less helium. It's going to fuse it into hydrogen. And when it runs out of helium, it's going to shrink. Again, because you're taking those outward arrows away and all we have are the inward pull of gravity. So it shrinks another time. So let's do that here. And in fact, it's going to shrink even more than it did before. Okay? And now you've got, it's even hotter than it was. I should probably even draw this guy smaller. And then it will expand again once it starts to fuse that carbon into nitrogen, right? But with a smaller star like the sun, this process only goes on a short time. I mean, we're talking maybe 1 billion years. So relatively short, right? I mean, it doesn't go through a lot of cycles of the shrinking and shrinking and expanding, because once it expands, it doesn't have enough gravity now to hold its shape together. So those outer layers, they are lost in what is known as a planetary nebula. Let me see if I can find one of those. Here we go. So here's a good planetary nebula. Okay? Oh, my eyes are like bugging me out here. Looks like a planetary nebula. So planetary nebula, it has those outer layers that are kind of moving away. I think I have some better examples here. And what's left over on the core of the planetary nebula is a white dwarf. I'm going to go back a slide because it says this might be the remnants of a supernova. It's got the shape that I want, but here we go. So here's a good planetary nebula. You can really see the shape of that here with the white dwarf in the middle. You see that? And there are all sorts of cool pictures of planetary nebula. If you go out there and just Google planetary nebula, you're going to see these. They're awesome. And they're called planetary nebulae because they're round and they represent, or they look like planet in shape, right? Here's another good example of a planetary nebula. You see that round shape with the white dwarf at the center, which it's kind of hard to distinguish where your white dwarf here is actually, but okay. So the white dwarf is just the core of the star, and it's no longer doing fusion. It's just got residual heat. So it's very hot, because remember, the surface temperature was a lot cooler than the core temperature. That's why these guys lie here, because they're super hot, but they're not real bright because they're very small. And then eventually they just cool down and go dark. And they're just chunks of carbon in space. And we call those black dwarfs. Black dwarfs are dead low mass stars. And that's the fate of our sun eventually, but not for